Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are starting third lecture of week number 3. In total, this is our ninth lecture for the course of wireless and mobile communication. In our previous lecture this week, we talked about interference, and we discussed that in cellular systems two types of interferences are very important. First one is called co-channel interference, and second is adjacent channel interference. And we discussed that how we can reduce the effect of interference and what are the strategies that can be incorporated in the system so that overall effect of interference is limited to acceptable range. Further, we discussed that interference limits the capacity of the system, and interference is actually major bottleneck in increasing the capacity of the system. In today's lecture, we are going to talk about two important concepts which are interrelated. First one is trunking and second is grade of service. Trunking and grade of service are two fundamental aspects that we use when we are trying to design a wireless communication system. Actually, this trunking is based on a mathematical theory which is sometimes known as queuing theory or trunking theory, which was proposed by a Danish mathematician named Erlang. And in order to honor the mathematician, one of the unit that we use in trunking theory, which is traffic intensity, that unit has been named after this mathematician Erlang. So we'll discuss about it when we talk about trunking in detail. So let us begin our discussion why we need trunking. In order to understand trunking, we must recall some of the important aspects related to wireless communication system. First thing that I want to mention is that in wireless systems, the number of users or subscriber of the system, they are relatively in large number as compared to available channels. So the number of channels that we deploy in any specific system, they do not match the number of users. So basically this channel need to be shared among the users. Second thing, we must note that if all the channels which are deployed in any wireless network, if all of the channel they are occupied, and in that situation if someone wants to initiate a new call, it cannot be entertained because there is no free channel. So in order to have a successful call, it is mandatory to have a free channel available in the system. And of course, when we try to plan a system, so we try to ensure that most of the subscribers they get the call connected whenever they want to make a call. So a good system is the one that ensures a call connectivity even at the peak loads. So in other words, a good system is the one in which the probability of blocking a call is very low. On the other hand, if we talk about subscribers behavior, so we see that the subscriber calling behavior is actually a random entity, because we do not know when a subscriber will start a call. The call can be initiated anytime in the day. It can be daytime or night, or so within 24 hours any subscriber can initiate a call at any time. So we do not have any specific time scheduled for the call, so it's a random phenomena. We do know that there are some peak times. For example, the office hours, they are generally peak time. The evening time, they are generally treated as peak times, where most of the people they try to call others, but still that behavior is random, because no one can predict how at what time a call would be initiated. Second thing, the duration of call is not constant. Different subscriber, they have they make call with different durations. Even a single subscriber, different calls from a single subscriber would have different durations. So there are some calls which take long time, but there are certain calls for which the duration is very small. Third thing, how many subscribers would attempt to make a call at certain time? It's also a random number, because for example, if you see a city like Karachi, and if I ask you how many subscribers would be calling in next 1 hour, so that behavior is unpredictable. So how many subscribers would be calling in next 1 hour or next 30 minutes is random, and at different days and different times you would see a different behavior. So what I want to say is that the subscriber behavior in wireless systems is actually a random phenomena, and that random phenomena coupled with the limited number of channel would make the system relatively complex. So we need a trunking theory, a mathematical theory, which actually deals with certain situation, and objective of applying that trunking theory to design such system is that we want to minimize the probability of blocking, so that all the users or at least most of the users, they are able to make a call whenever they intend to do so. So what is trunking? Trunking is a concept that allow a large number of users to share the relatively small number of channels in a cell by providing access to each user on demand from a pool of available channels. So for example, if in a certain cell 10 channels are made available, if a user tries to make a call, so one of the channel is allocated to that user. If second user tries to make a call, the second channel will be made available to that second user, and so on. And as soon as one of the user ends its call, the channel becomes free, and it becomes it's available for it becomes available for other users as well. So for example, if someone makes a call of like say for example 2 minutes, and after 2 minutes his or her channel would become available, and at that a new user initiates a call, so that channel can be allocated to the new user. So basically the channel is shared among the users, and it's allocated on demand basis, so that most of the users, they are able to make the call. So basically our cellular system, they rely on the trunking to accommodate large number of users in a limited radio spectrum. Important thing is that how we can design such system. So basically we are dealing with some random phenomena, because as I said, the behavior of subscribers is random. So we do not exactly know what would be the behavior at certain time. So in that the designing process in that case is actually based on the statistical behavior of users. So generally we need to analyze what is the statistical behavior, and we design the system on such basis. I mean statistical behavior, we refer to different types of statistical average. For example, one of the average that we use is what is the average duration of call that is made in a day. So average duration would be different than an individual call, but on average there will be a number. So we design the behavior on the basis of those averages. As I said, cellular systems, they are based on trunking, but these are not the only systems which are based on trunking. There are certain examples in communication system which rely on the trunking theory. So for example, if you see a traditional landline phone, the public switch telephone network, they also rely on trunking. For example, you have a exchange here, this black box here, and another exchange at some different location is available on the other side, and this exchange provides connectivity to a number of users. Say for example, it provides connectivity to 10,000 users. Similarly, the exchange on the other city, it also provides connectivity to 10,000 users. This is just a random number. But there is a possibility that a user from city A also wants to communicate to a user of city B. In that case, it has to go take a connection between these two exchanges. So generally there are limited number of connection available between these two exchange or central offices. So this one, for example, this user wants to connect this first one, so it will connect to the central office. The central office will connect to the central office in the city B, and city B will connect to the other user. The number of subscriber line which connects these two, these are actually limited. So for example, if there are 10 lines, so these 10 lines need to be shared among all those users who want to make a trunk call. We call it trunk call because it has to go through this trunk. These central lines, they are generally known as trunks. So these trunk lines, they provide access to users on demand basis, like we do in wireless communications when we try to allocate the channels. Similarly, in IP networks, where we generally deal with data communication, different devices, they connect to routers, and the routers are interconnected with kind of central lines or trunk lines which provide connectivity between different routers to connect different networks. So there is a network A and network B, which have two routers which are connected to through a trunks. Maybe there may be one or more trunk lines. So whenever a user from network A intend to communicate to a user in network B, the data or voice, it has to go through these trunk lines, and these trunk lines, they are allocated on the basis of they are allocated on demand basis, and the designing of these lines is also based on the trunking theory or queuing theory. So what I want to say that this trunking theory is very common in communication systems, and different systems are designed on the basis of trunking, so that we want to optimize the use of resources. So we design the system so that we allocate the number of trunk lines in such a way that the overall probability of not communicating or not being able to communicating or denying access is at the minimum level. Okay, so this was the basic introduction regarding trunking. So basically we use trunking to determine the number of telephone circuits or number of channels which need to be allocated in certain area. The main objective is that we want to have minimum probability of call blocking. Moreover, if we try to accommodate large number of channel, it will be wastage of resources as well. So it's kind of optimization. For example, if a certain region requires 15 channels to be allocated and we allocate 100 channels there, so we will be wasting our resources of 85 channels that could have been utilized at some other networks. So we try to optimize the situation so that we get the optimum results with the lower probability of blocking. So in principle, what happens when you have more number of channels? In that case, the people will be having lesser probability of finding all channel busy, and in that case the probability of blocking is at the lower level, and so that we get a better grade of service, which is called GOS. In trunk system, or basically we are talking about wireless system. So basically there are two possibilities of handling when all channels become occupied. So there are two types of trunk systems. When a user makes a call request and it finds all the channel busy, so one possibility is that the system blocks the user, and it does not give access to the system because there is no free channel. So we call it a blocked call cleared system. So whenever our user is blocked, it is removed from the system, but it can make another call if it intends to. The second user the second type of system is that in which when all the channels are busy, the blocked caller is put on a hold. So we call, in queuing theory or trunking theory, we call it's put in a queue, and it keeps on waiting until a new one of the channel becomes available. As soon as a channel becomes available, the call is transferred to that particular channel. So this type of system is called queued system. So basically in wireless system we talk about these two types of systems. First one, block called clear, which refers to the condition when there is when all the channels they are occupied, the new caller would be denied access to the system. And second is block called queued system, which refers to the condition when all the channels are occupied, the new user will be put on hold or put in a queue for waiting until one of the channel becomes free. So at this stage I want to define a term which is grade of service, because we need to have some parameter through which we can measure the performance of a trunked system. So basically that parameter is named as grade of service. So grade of service is actually a measure of the ability of a user to access the trunked system during the busiest hour. When we are trying to design a system, we generally define a specific grade of service. Actually the grade of service is defined in as opposite to the ability of being access to the system. Basically we define grade of service as the probability or likelihood of call being blocked. I said there are two types of system. One system is that in which a call is blocked, and other system is that in which a call is queued with a delay. So so there are two types of system. So grade of service is basically the likelihood of call being blocked if we have blocked call cleared system, and or it is defined as the probability of call getting a delay larger than a specific time. So basically this grade of service is a benchmark. It provides a benchmark in order to design the system, and the designer has to choose a specific number of channels so that a specific grade of service is obtained. So we want to maximize capacity of the wireless system so that the proper number of channels are allocated in order to meet the GOS criteria, whichever is defined in that particular system. So this is how we measure how we represent the performance of a wireless system, a trunked wireless system. There are some specific terms that we use in defining different types of trunking systems. These terminologies are generally used in trunking systems. So as we are applying the trunking system in in our wireless design. So we must understand these terms. First of the important term is the traffic intensity. What is traffic intensity? This is basically this refers to the channel time utilization. So how much occupancy is there when we have specific type of channel. This traffic intensity is from a perspective of SI units is a dimensionless quantity because it does not have any units, but we measure it in Erlangs, where we have Erlang, a specific definition of Erlang that I will be explaining in a while. So traffic intensity is one of the important parameter which is used to measure how much load will be there in a specific system and how much traffic need to be carried through that particular type of system. As I said, an important unit we have to define, which is Erlang. Erlang is basically a unit of traffic intensity. Dimensionless is primarily a dimensionless quantity. How do we define the Erlang? So one Erlang is defined as the amount of traffic which is carried by a channel which is completely occupied over a specific period of time. For example, if we have a call of 1 hour and it goes through a channel exactly in 1 hour, so that thing would show an intensity of 1 Erlang. In order to understand what is Erlang, let me give some more examples here. For example, if we have two calls each of 15-minute duration, so in a particular system or for a particular channel, two calls are made for each of 15 minutes, so there will be a total of 30 minutes of call duration, and remaining 30 minutes, because 1 hour has 60 minutes, so remaining 30 minutes channel is not utilized. So we have channel utilization for 30 minutes and no utilization for remaining of 30 minutes. That means half of the time the channel is being utilized. So that means the traffic intensity in that particular case is actually 0.5 Erlang. Let me take another example. If we have two calls of duration of 0.5 hours, 0.5 hours means 30 minutes. So one call is of 0.5 hour and another call is of 0.5 hour. So in total these two calls would end up with a utilization of exactly 60 minutes. So in 1 hour there is 1 hour utilization of the channel. So the total the capacity would be 1 Erlang. Let us take another example. If we have 4 calls of 30 minutes duration, so there are 4 calls which are made for 30 minutes in an hour. Of course 4 calls cannot be carried through one channel, there may be more than one channels, but assuming that there are sufficient number of channels and we have 4 calls of 30-minute duration each. 4 calls of 30-minute duration means the total call duration will be 4 into 30 minutes. 4 into 30 minutes would be 120 minutes, and this call has been carried over a channel over the system in 1 hour. 1 hour means 60 minutes. So this 120-minute call duration over 60-minute utilization would result in a traffic intensity of 2 Erlangs. So basically Erlang shows how much call is offered in particular system, and it is actually related to the number of call as well as the call duration, and we generally measure it over a specific duration of time. For example, in the Given examples what I have shown here, I have observed the calls over 1 hour duration, but it's not necessary that in all cases we define the calls over 1 hour duration. At certain instance we can choose to define it in other time units as well. So basically traffic intensity is one of the primary parameter which shows how much traffic has to be carried by the system, and we generally measure that traffic intensity in Erlang. There are certain other definitions as well. One of the important definition is setup time. In some cases there is some setup time required to gain access to a channel. For example, for block called queued system, if all the channels are occupied, the user has to wait for some time. So there will be certain time that would be required for user before it gets access to the system. So this time which is required to allocate a channel to a system, this is named as the setup time. A block call is the one which for which the request cannot be entertained because of occupancy of channel. For example, if all the channels are occupied, so and a new user wants to initiate a call at that instance, in that case it will not be given access to the channel. So that particular call will be named as blocked call, or sometimes we call it lost call. So all those calls which cannot be given access to a particular system would end up in this category. As I said earlier, when a user makes a call, generally a call lasts for a specific duration of time, and for that particular duration of time the channel is occupied by that particular user. But because that time is random, so different users or different calls would be having different times of occupancy. But in order to design the system, we generally work on the average time our channel is occupied, or in other words, we work on the average duration of the typical call, and this average duration of call is named as holding time. Typically we represent this holding time with capital H, and as it's a time, so it's measured in the units of time, which is seconds. So holding time is actually average duration of a call in particular system. Okay, next definition is load. Load is also traffic intensity, but traffic intensity is generalized term. When we use load, by load we generally mean that we want to incorporate all the traffic intensity which is offered to any specific trunk radio system. So it's basically load represents a total traffic intensity across the entire trunked radio system. Of course, because it's traffic intensity, we generally measure this load in Erlangs. Next is the request rate. As we know that when we have system, so there will be a number of users that will be trying to initiate a call. So whenever a user tries to initiate a call, it will send a request to initiate the call to the system. So a system would typically receive a specific number of call requests in unit time. So basically this request rate, it is actually represented as the number of call requests per unit time. So if we are the time unit we are using is seconds, in that case the unit will be calls per second. But we know that call is actually not as standard as a unit, so therefore we generally use the unit of 1/second, which means second inverse. So this request rate is actually represented in units of second inverse, Typically we denote this request rate by symbol lambda. Next terminology is grade of service, but we have already defined grade of service. So basically grade of service is defined in two different ways depending on which type of system we are working on. So if we have block called cleared system, in that case grade of service represents a probability that a call will be blocked and will not be allowed to use the channel. For the block called queued system, in that case the grade of service is defined as the probability of call being delayed beyond a certain period of time. For example, if we define a time period of 30 seconds, the grade of service will be representing the probability that a call is queued for 30 seconds or more. As I said, traffic intensity is a general term that we use. Sometimes we use a term which is called traffic intensity per user, because in typical situations there will be a number of users in the system. So sometimes we are interested in how much traffic intensity is generated by a single user on an average basis. So we are denoting this traffic intensity per user by AU, and of course it's a type of traffic intensity, so it will be measured in Erlangs. So by concept, traffic intensity per user is actually the overall traffic intensity or average traffic intensity that a single user generates. Mathematically, we define a traffic intensity per user as the product of call request rate and the holding time, because call request rate gives number of calls per unit second per unit time, and holding time is the number of seconds that call remains. So when we multiply both of them, so eventually we get our overall traffic intensity. If you go back to the definition of Erlang, this is how we calculate the traffic intensity. We multiply the calls with the total occupancy divided by the period over which we are trying to evaluate. So when we are evaluating the same thing for one user, so that thing becomes the traffic intensity per user. So these are few terms that are commonly used in trunking theory. These are not specific to wireless systems, but all trunking or queuing systems they generally use these terms. And different parameters that we defined here, they are interrelated. So let me try to establish the relationship between different parameters. First of all, the important parameter is traffic intensity per user that we defined right now. Traffic intensity per user, if you see, by definition is actually call request rate, which is represented by lambda, and the holding time, which is multiplied by the holding time, which is represented by h. So we have very simple relationship for traffic intensity per user. So AU is actually lambda multiplied by h, where lambda is the call request rate represented in number of calls per second, and h is the holding time. Generally, when we talk about a system, so there will be more than one users in the system. So let us assume that there are users in a system. We don't care about number of channels right now, how many channels are there. So in that case, what will be the total load offered to the system? So we can, so one user is actually generating this much traffic intensity. This is AU, and if you multiply it by the number of users, which is represented here by U, so we will get the total offered traffic intensity. At this point, I want to clarify that this is the offered traffic intensity that is offered to a specific system, which is generated in a system. it's not necessary that this entire traffic intensity is carried out by the channels. For example, let me take a very simple case that we have one channel and we have a total offered traffic intensity of 2 Erlangs. So 2 Erlang traffic intensity cannot be carried over one channel. So eventually the total offered traffic intensity will remain 2 Erlangs, but the actual intensity which goes through the channels or which goes through the system is actually limited by the number of channels. So when we refer to this total traffic intensity, we generally taking it is without reference to the channel. So this is actually the intensity offered to the system, not the intensity which is carried by the system. So you must make a clear distinction between these two things, because our systems, they have a finite number of channels. So eventually we sometimes have to calculate the traffic intensity on per channel basis, which is represented as AC. So if we have C number of channels in the system, so number of channels are denoted by C, so then what will be the total traffic intensity per channel? So you can simply calculate it by dividing the total offered traffic intensity by number of channels. So this is the simple definition, because we want to calculate the traffic intensity on per channel basis. Or in other words, we can, because this total traffic intensity is product of number of users and per user traffic intensity, so we can write it as U into AU divided by C. So this is the traffic intensity that will be represented on per channel basis.